Okay, so welcome back to the Strength Pheno seminar series. We are very happy to have Irene and Luigi speaking to us today. So let's start with Irene, who will tell us about the desert and the swampland. Yeah, please take it away.
Okay, thank you very much, Kerry and Marcus, for the invitation. So my plan today is to talk a bit about this recent work with Cody Long, Miguel Montedo, and Kunrun Bafa, which is about the desert and the swampland. So let me start with the swampland. I mean, of course, probably everybody in this audience already knows what it is. We use the word swampland to refer to those EFTs that cannot be UV completed in quantum gravity. And in recent years, there's been a lot of activity in this regarding the swampland program, trying to make precise what is the difference, what distinguishes this swampland from the landscape, which are those effective field theories that can arise as low energy descriptions of quantum gravity. Now, one of the things that I like to emphasize in this picture when I did it is that the landscape is smaller than the swampland. Okay, how small? Well, actually, what we expect is that the landscape is finite, that there is only a finite number of EFTs, while the swampland is infinite. Like there could be infinitely many effective field theories that seem consistent in quantum field theory, but still cannot be embedded in quantum gravity. So this is like the basic features, no? That's one of the basic features that would distinguish both, no? Like to think of the landscape or the swampland. And this is the feature in which I'm going to focus in this talk. Okay, in particular, so we expect to have a finite number of quantum gravity vacua, which are valid at least up to a given cutoff. And this implies that we would also expect to have a finite number of massless fields. Okay. So the question that originated our work was to see if we could try to give an upper bound on the number of massless states that we can have in a quantum gravity theory. Okay. Okay, so you could try to give an upper bound on the number of massless states by using black hole arguments. Like, for example, you can think that maybe having infinitely many states can yield a violation with entropy bounds, because you could put many states inside a box, and since the entropy of the box cannot be larger than the entropy associated to a black hole of that size, this is going to give a bound on the number of like species, no, that we can put in the box. However, the smallest black hole that we can trust in the theory is given by the cutoff. So actually, this is not really giving you like an upper bound on the number of fields, but a relation between the number of fields and the cutoff. So everything is fine, and there is no violation with entropy bounds as long as the cutoff of the EFT also becomes smaller as we increase the number of massless modes. And in fact, we can make this number arbitrarily large as long as the cutoff goes to 0. Okay, and this is precisely what happens at the infinite distance boundaries, right? So when we move in the field space, what we observe is that when we go to the infinite distance boundaries of the moduli space, we get this infinite tower of states that become light as dictated by the distance conjecture. And then everything is consistent, because even if I get more and more states, the cutoff is also going to 0, because the quantum gravitational effects become important. Okay, and the EFT completely breaks down. Okay, one can actually, I mean, the typical towers that we get, which are actually conjectured to be the only ones, are Kaluza-Klein towers, sort of Kaluza-Klein towers, or stream modes. And in both cases, actually, you can try to compute what would be this species scale, no, this quantum gravity cutoff, just by the structure of the tower. And in the case of a KK tower, indeed, what you get using this formula, right, this species scale, is that the species scale is equal to the Planck mass of the higher dimensional theory, which is consistent with the fact that we are decompactifying and quantum gravitational effects become important at the Planck mass of the higher dimensional theory, which can be lower than the Planck mass of the lower dimensional theory. And in the case of the string modes, what we get for the species bound is the string scale, no? Which is also the scale at which quantum field theory breaks down, and we need to go to string theory. Okay, so this is what happens at the boundaries. So clearly there is no lower bound for the cutoff. Okay, it can go to 0. But the question is whether there is an upper bound. Okay, so how much we can push this cutoff. And this will happen in the interior of the modular space. Okay, so it's the opposite of studying the boundaries. We really want to study the deep interior of the modular space. And it's interesting because it could yield a bound on the number of massless modes. Because the larger this species bound is, the larger we can push the cutoff, the smaller the number of modes we can have by consistency. Okay. So the question that we are going to address in this work is whether we can determine the maximum value of the cutoff, which will happen at the deepest interior of the modular space. So whether we can push this cutoff up all the way to the Planck mass, and whether we can extract from this any bound on the number of massless modes. Okay. So in the deep interior of the modular space, what we expect is what we call the desert scenario, in which everything that can get a mass is as massive as possible, right? We expect to have maybe some massless modes and then some desert up to the massive modes, which are pushed as high as possible. Okay, so we are looking for the maximum value of the cutoff. And in that case, then we will expect that the species scale is mainly dominated by the massless modes, okay, because there are no light species. Okay, so the goal is to determine how this cutoff, what is the maximum value of the cutoff in this modular space. And we'll do this by focusing on BPS objects. Okay, well, of course, it's very hard to keep track of all the complete spectra, but at least we can do it for BPS states. And this is going to give us an upper bound on the cutoff, okay, because at least we know that at that scale, the AFT is going to break down. Okay, so an estimation of this maximum cutoff is going to be given by maximizing this, the minimum value of the possible BPS states. And here with BPS states, I also mean maybe non-BPS states that arise from wrapping BPS states. Okay, so everything is correlated to having some original BPS object. Okay, so let's do it. Let's try to analyze what is this cutoff. So let me first, I'm gonna tell you briefly what happens in the case of 32 and 16 supercharges, and then we'll move quickly to the most interesting case of 8 supercharges. Okay, so for 32, of course, I mean, we can, as an example, we can consider M-theory and type 2A and type 2B in 10 dimensions. And in all these cases, this cutoff is of order the Planck mass, right? In M-theory, it will be set by the M2 branes. In type 2A, we have all the D branes. And here we can already see that there is this structure in which we have some like electric states and magnetic states. And then the point in which the gap is takes the maximum value is where all these towers of states cross. Right, so it's going to happen around GS of order 1, and then the cutoff will be also of order 1 in Planck units. And for the case of type 2B, it's going to be set by PQ strings, and one can check what is the point that minimizes, that minimizes the volume here, so it maximizes this tension. And this is still going to be of order Planck mass at some cubic root of the Tadpole. Okay, so this is for 32, not so interesting. Let's go to 16 supercharges. Of course, in 16 supercharges, we have more types of states. If we focus on the BPS ones, they are going to form a cone, which will also be present in the examples of 8 supercharges that I will show you later. And we can distinguish the 3 types of BPS states, depending on whether they become massless at finite, infinite distance, or nowhere. Okay, so we have field theory states that become massless at finite distance, the asymptotic towers that will become massless at infinite distance, and black hole states that remain always massive. And just to give you an example, if you consider a circle compactification of the heterotic without Wilson lines, one can plot the masses and see that the gap is given by the intersection between these field theory states, which is the blue line, okay, with one of the asymptotic towers, okay. And this happens around 0.25 times the string scale. So I'm showing you this because it will be important later on also what are the states that are setting the scale. Okay, so here we can see that already the field theory states are playing an important role. And this is the quantum gravity, this is the cutoff that we will be talking about. Okay, you could also try to incorporate in the field theory states in your EFT and talk only about the cutoff given by the asymptotic towers, but this is always around the Planck mass. Okay, so let's go to the most interesting case of phase supercharges. First, I'm going to show you some estimation of what is this gap, both for 6D, 5D, and 4D effective field theories. And then we will go to actual examples. So for the case of phase supercharges, we have for sub-VP states, which will be given, the mass will be given by the volume of the cycle that they are wrapping. And in the case of 6D n equals 1, which comes from F theorem Calabi-Yau threefold, they correspond to BP strings that have a tension in Planck units given by this combination of the Kähler parameters. Okay, because these are the volumes of the two cycles. And since it's in Planck units.
Are you allowed to ask questions in the seminar or only at the end of the talk?
As you wish, for me it's fine.
Oh, I don't know. I don't come so often, so I don't know.
It's up to the speaker.
Oh, it's up to
ask questions.
Yeah, so with eight supercharges or less, then there are loop corrections to the Planck mass, I would guess. And then isn't it just a one loop running of the Planck scale? The species scale just comes from one loop running of the Planck mass, or so no, is there some inconsistency to even check? I mean, in the sense that if you have n fields running in one loop, you will get the species scale just from one loop running. No,
well, it's not gonna be so easy. So the thing, well, first, I mean, the BP states are going to be independent, right, of the hypermultiplex sector. So the mass of the BP state in Planck units is independent of the value of the volume, which is the one that will receive corrections. Right?
So I thought maybe I misunderstood what you're trying to do. I thought you were saying that you're trying to get a bound in a number of massless modes by saying that species scale associated with a number of modes must be some cutoff scale in the theory. And you say that that cutoff scale should be associated to some new degrees of freedom, some tau of new degrees of freedom. And you say, okay, there should be BPS states. So therefore, you say, as I understand, you're trying to say something like,
I'm going to do the other way around. I'm going to forget right now about the species bound. I mean, this is telling me that there should be some cutoff that depends on the number of fields, but let's forget about it and let's study in practice, like what is the maximum cutoff that I can obtain by focusing on the BP states. And then I will obtain some value for this cutoff that depends on the number of fields, and I will compare it with the species bound. And you will see what happens then.
So is the logic like this, saying that the species scale should always be some new UV degrees of freedom, like BPS states? And then you're saying there cannot be an infinite number of massless fields, but having very massive BPS states.
Yeah, exactly. If you try to push it.
Yeah, but then I think I was saying, like, if you don't have much supersymmetry, then if you have an infinite number of massless fields, there will be one loop running of the Planck scale that will automatically guarantee the species scale will be a strong coupling scale, independent of whether the BPS states or not. Or, do you see the point or not?
Yeah, you're thinking of like flowing to the infrared and saying,
yeah, just like there's a kind of argument you can derive the species scales just by calculating the one.
So that's what I tried to say at the beginning. I mean, if you just take the species scale, you don't really get a bound on the number of fields because you can always decrease the cutoff.
Yeah. And
that's fine. So you cannot get around that this way. We'll see that there is a discrepancy with the species bound, and that's how we will recover the bound.
Okay, all right. Thanks. Yeah. Okay. Yeah, sorry, I jumped the gun. Yeah.
No, it's okay. Okay. So for the case of 6D n equals 1, we have to study the tension of these strings. And if right now I just make a naive estimation, I mean, of course, the concrete value is going to depend on the intersection numbers of the Calabi-Yaus. But if I make some naive estimation that the the sum of the entries, no, of these intersection numbers scales with n, with the number of, with h11, no, with the number of massless, number of entries, then one would get that this condition of the volume set to 1 implies that T has to scale this way with n, and if you plug it back on the tension for the string, one would get that the BPS gap scales with n to the -1/4. Okay, this is assuming this behavior of the intersection numbers. Now, in 5T n = 1, you can do the same. The BPS particles will come from wrapping M2 branes, and if you make the same type of assumption for the intersection numbers, then we will get that the BPS gap scales with -1/3. In 4D, you can do the same, and you will see where I'm going. Again, now it's better to consider the complex structure sector, because otherwise we need to take into account corrections, because we are going to the deep interior of the moduli space. And again, if one makes the same type of assumption that this sum over entries, no, scales with n, and there are no cancellations or anything like that, then in this case, the BPS gap will scale with n -1/2, which means that in all the cases, by making this assumption, one gets that the BPS gap scales with, sorry, this is -1/d-2. Okay, so this is precisely the behavior given by the species bound, which is kind of surprising. I mean, why this naive estimation gives you the species bound result? But what I'm going to show you now is that if we now take actual Calavillao data and actual examples, we are going to see that this estimation was too naive, and we actually recover a bigger slope for the cutoff. Okay. Okay, so this is I hope to finish this quickly. So I'm just going to show you now some actual results from considering actual Calavillaos. So I'm going to focus on the case of 6T n = 1 theories. Okay. This is the tension of the BPS strings. And now, I mean, the BPS objects are going to form a cone, because two BPS strings that are BPS are also mutually BPS. And the cones of these charges is equivalent to the Mori cone of the base. Okay. So in order to compute the maximum gap, we need to know the Mori cone for these Calavillaos. And this is a hard question in general, but we can take, for example, this list of Morrison and Taylor, in which they classify all possible toric bases and give the Mori cone for all possible elliptic triforks that have a toric base. Forget now some technical things. The point is that in the end we have 34, almost 35,000 Calavillaos to play with. Okay. So we have some algorithm in which we are trying to find the maximum gap. So we need to find the maximum value for the minimum value of the value of these curves, which is set in the BPS mass. And since the overall volume is homogeneous on the Kähler parameters, we can rescale the problem to translate it to something simpler, which is instead of fixing the overall volume to 1 and maximizing these curves volumes, what we do is to fix the minimal curve to have volume 1 and minimize the overall volume. Okay, so we just need to minimize one function. And this is equivalent to say that what we need is to find the minimum value of the overall volume, the volume of the base, sorry, within the stretch Kähler cone, okay, which is defined as having all curve volumes bigger or equal than 1. And this is going to happen at the boundaries of this stretch Kähler cone, where the curves have volume 1. Okay, so we just need to evaluate in the end the volume there and find the minimum value. Okay, so if we do this for all these 35,000 Calavillaos, this is the result that we get. We have that indeed the BPS gap, the cutoff, is decreasing with the number of massless fields with H11. There is some dispersion, but still there is like some clear tendency that is the best fit is given by this curve. So the volume scales this way, and therefore the BPS gap scales with H11 to 0.7. Okay, this is the result. Let me also mention that these cutoff, these BPS states are typically given by curves of negative self-intersection, so they correspond to field theory states, like strings that become tensionless at finite distance, but still they are not mutually local among each other. Okay, so now we can compare this with the species bound. Okay, on one hand, it's similar in the sense that it decreases with the number of fields, but the slope is different. Okay, so we can represent it in terms of all the massless modes, taking into account also the tensor multiplets and so on. And the slope for the BPS gap has a bigger slope than what the species bound would tell us. Okay, so this means that the naive estimation we made of the intersection numbers is actually not quite right in actual examples. Now, what is going on here? Well, I mean, every time we study this species bound at asymptotic boundary, at the asymptotic limits, we always get that the species scale is not just a bound, but it's really telling you some new physics that appears, that there should be some states there. And what could happen, I mean, a possible resolution is that indeed the BPS states are not the lightest ones that we have, and maybe the species scale can be reproduced if one considers non-BPS states like K towers and so on. Okay, so that would be consistent with having this BPS gap above this species bound set by other lighter fields. Now, the point is that this is only consistent for some range, because since they have a different slope, they are going to cross at some point. And if we want to explain this by saying that the BPS gap is going to be bigger than the species scale set by Kekimos or other things, then this is only valid up to a finite value of the number of massless modes. So this possible resolution would give an upper bound on the number of massless modes that we can have. Okay, which is also consistent with all the studies, no, that show that there is only a finite number of electrically fiber Calabi-Yau threefolds. Okay, so this is a way to recover this upper bound on the number of massless modes, which is not, you cannot recover only from the species bound itself. So just to finish, let me make some comments about the relation of this actually with the Tadpole conjecture, which seems very far away, but actually there is some interesting relation because it's the same type of optimization problem that we are addressing here. So just, I mean, maybe this is a bit quick for those that do not know what the Tadpole conjecture is, but the point is that there are some works showing that maybe it's not so easy to stabilize all moduli for when we have large number of moduli without getting into trouble with the Tadpole conditions. Okay, so there is this conjecture that says then the number of flags that you need to stabilize all the moduli is going to be going to scale as h2,1 such that it will not allow you to satisfy the Tadpole condition. Now, if one wants to check this conjecture in the large complex structure limit, this is going to map to the stretch scalar cone of the mirror. And as remarked by Eric, checking this conjecture reduces to finding the minimal value of the volume within the stretch scalar cone. Because in the large complex structure limit, this flux number is going to scale as the volume plus other terms. So by checking this, I mean, the crucial part is to understand how this volume and these intersection numbers behave and how they grow with the number of moduli. So it's the same optimization problem that we just did, like finding the minimal volume in the stretch scalar cone. It's just that we were interested in 60. So even if we were considering Calabi-Yau threefolds, we were interested in the volume of the base. So in order to really connect with the Tadpole conjecture, we will need the volume of the overall Calabi-Yau. But already here we can see that the volume of the base scales even higher than linearly, no? So it scales with 1.4. So it goes on the lines of the Tadpole conjecture. If we did the same for 5D, then it would really be exactly the same optimization problem, because in this case, the BPS gap is really given by the overall volume. And if it happens the same, that the BPS gap gives a larger slope than the species bound, it would mean that the overall volume scales linearly or higher with the number of fields. So indeed, it would satisfy also the Tadpole conjecture. Okay, so it would be interesting to check in other setups in 5D and 4 dimensions whether it always happens that this maximum BPS gap scales with a power on the number of massless fields, which is bigger than the one set by the species bound. And if that's the case, then this would imply this Tadpole conjecture, where the saturation, I mean, if this scales exactly as the species bound, would exactly give rise to this Tadpole conjecture. It's the linear behavior of the Tadpole conjecture. So this is something to study more in the future. But let me just, because probably I'm out of time, so let me conclude. So we have analyzed this maximum value of the cutoff set by the BPS states in large classes of supersymmetric compactifications. And indeed, this is given by the, I mean, it has a dependence on the number of massless modes, but it happens to have a bigger slope than the species bound, which is quite surprising. Now, this, I want to say some cautionary remark in the sense that if we just take these genericity arguments that we make sometimes about intersection numbers and so on, they actually give some result which differs from actual data and which actually surprisingly would coincide with the species bound. So that's something I don't understand why it's there is this coincidence. But yeah, one should be careful when doing that. I think it's interesting to study this further and do this type of analysis in the deep interior because it can also provide evidence or disprove the Tadpole conjecture. Let me point out also that this is just a tendency of all the Calabi-Yaus, right? It doesn't mean that there is no particular examples that give different values. And yeah, this is the, I mean, this maximum gap happens at the deepest point in the moduli space. So it's the opposite as studying the asymptotic boundaries. Let's try to continue studying these properties because at least in supersymmetric compactification is possible and can teach us many things. So thank you for your attention.
Thank you, Irene, for the great talk. Are there questions for Irene? While we are waiting, what assumptions that went into the estimate on the cutoff based on the intersection number are actually violated in specific examples?
Say again, sorry, I couldn't listen.
So what assumptions that went into the estimate of lambda based on the intersection number that are violated so that you get a different slope?
You mean this naive estimation that gives the species bound? Or...
Yeah. So the actual example gives you a different slope. So some
the actual example, exactly. So what goes wrong is that, yes, this, so that the number, this sum of the intersection matrix grows as n. Like you can just consider, so that it's kind of diagonal and you just have to sum the entries. Mm-hmm. So these intersection matrices are not diagonal, and then when you compute the inverse, it really matters this of diagonal terms. So this growth, I mean, if you compute the sum of this intersection, it grows faster than n.
Faster than
in
n.
actual examples. Yeah, it's faster.
Okay.
And that's what gives a bigger slope.
Okay. Thank you. Any questions for Irene? You are right on time.
Surprising.
Okay.